grade 12s. We are still under topic 3, which is curve sketching in this applications of calculus topic. We are doing the last kind of piece of the puzzle before we start curve sketching, and curve sketching is probably one of my favorite sections. So we're doing asymptotes, which is topic 3.2, and then finally we'll be on to 3.3, where we can actually draw some pretty cool functions. So there's a couple of different types of asymptotes, and we're going to go through each one of them one at a time with some examples. Now, ones that you should know from last year are vertical asymptotes. We've seen them in normal maths as well. Now, vertical asymptotes exist when there's something called an asymptotic discontinuity. Now, those aren't actually words that you need to know in AP Maths, but they're pretty cool. So this exists where there is an asymptotic discontinuity. Now, what does that actually mean? Because you kind of say, well, it's a vertical asymptote because there's an asymptote. So what actually causes an asymptotic discontinuity? This exists because within the function, x is not allowed to be equal to something. So this occurs because x is not allowed to equal a certain value. Now, why would you not allow it to be equal to a certain value? And this always comes back to the fact that the denominator is not allowed to be 0. Now, there's actually two different kind of situations that can arise if a denominator is going to be 0, and I'm going to show you in each of these examples. So a vertical asymptote exists because there's something called an asymptotic discontinuity, because basically there is an x value that is not allowed as part of the domain because it makes the denominator 0. So if we look at example 1, which is 2x over x subtract 3, I know that x subtract 3 is never allowed to be equal to 0, which means I know that x is never allowed to be 3 in this function. If x was 3, the function is undefined. So therefore, the function is undefined at x is equal to 3, and that means you have an asymptote. So therefore, there is a vertical asymptote at x is equal to 3. Okay, now there's a kind of little bit of T's and C's apply, and that's what our example 2 is going to look at. And then we're going to go back to example 1 and just write down something extra. Example 2 says, what happens if you have x take away 4 all over x take away 4x plus 3? Now what happens here is, can you simplify? We should always ask ourselves, can I simplify the function first? That should always be our first question. Can we simplify the function first? And in this particular case I can, because if I put a bracket around x minus 4, which I'm allowed to do, remember you're always allowed to put a bracket around something, that means that that will cancel, which means this actually simplifies to 1 over x plus 3. Now what does this mean? If I go back to the original function, there are two values that I'm not allowed to have in my domain. Well, there's two values where this function will be undefined. So don't think that because you've cancelled out the x minus 4 that the number 4 is now magically allowed in the domain. So I'm just going to write myself a note here. The original function dictates the values for x that are not allowed in the domain. So the original function dictates the values for x that are not allowed in the domain. I'm not really, yes, I suppose they're not allowed in the domain because the function will be undefined at that point, and so the domain cannot include them. So in this particular example, you're not allowed to have 4, and you're not allowed to have minus 3. However, there's two different things happening here. Because you could cancel out this x minus 4, what happens is x is equal to 4 is not an asymptotic discontinuity, and it's not therefore an asymptote. And that's because, so I'm going to say but dot 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 dot, the limit as x tends to 4 of g of x is equal to the limit. Remember, when you're finding out limits, you first simplify. So I find the limit of the simplified function, and guess what? You can actually find this limit. This limit is 1 over 7. So therefore, because the limit exists, x equals 4 is a removable discontinuity. So these probably should be ringing bells from last year. Discontinuity. When you can cancel out the problem, if there's a part of the domain that is not allowed, but you can remove that problem through simplification, you always get a removable discontinuity. The reason being is that you can find the limit. With a removable discontinuity, remember that means that the graph is going to tend towards this, and this is actually a hyperbola, so it's going to tend towards this 1 over 7 and tend towards this 1 over 7. So the limit is going to exist, and the moment the limit exists, you're going to get a removable discontinuity. For an asymptote, the limit does not exist, and so only denominators that cannot be simplified away form an asymptotic discontinuity because the limit doesn't exist. So I'm just going to write myself a note here. So if a factor in the denominator can cancel, so if a factor in the denominator can cancel away, this forms a removable discontinuity. And I hope that you understand it's because you actually can find the limit. So this is not an asymptote. So really important, I think that says discontinuity, really important, not every single factor in the denominator causes an asymptote. If you can cancel that factor away, it forms a removable discontinuity because the limit exists. It's only when the limit does not exist that you have an asymptote. So I'm going to say, but x is equal to negative 3 is a vertical asymptote. And the reason is because the limit as x tends to negative 3 of g of x does not exist. And that's because even if you simplify it to that, you still can't put in negative 3. So when the limit doesn't exist because of a denominator as a problem, you get a vertical asymptote. If you can cancel the problem away, so it means that that value is still not part of the domain, so you still are not allowed to be equal to 4, but you can actually get rid of that problem, you form a removable discontinuity. So this actually would be a hyperbola. If you think about it, that's a hyperbola. Fairly easy hyperbola for us to draw. It just has a hole in the graph because it has a removable discontinuity at 4. Okay, so that's vertical asymptotes. Really nice and easy as long as you get your head around this idea of the difference between a vertical asymptote and a removable discontinuity. So what's our second type of asymptote? There are 3 that we do. What's our second type, which we should remember from grade 11? The line y equals c is a horizontal asymptote of f. If. Okay, now what causes a horizontal asymptote? It exists because if you tend x to positive or negative infinity of a function, if the graph tends to a constant, then the horizontal line will be a horizontal asymptote. So let me show you what we mean here. In example 1, I've got h of x equals x over 2x squared plus 1. If you can find the limit as x tends to positive or minus infinity, it doesn't really matter which one, of x over 2x squared plus 1, if we can work this out and get a number, it means that as x tends to infinity, this graph will be tending towards that number, which means it tends towards that line. Now, not all graphs have a horizontal asymptote, so once we've done some examples, we're going to see when they will exist. Now again, I think we might be a bit rusty on this. I don't know if you remember, but whenever you're taking the limit as x tends to infinity, you divide by the highest power of x. So you divide the top and bottom by the highest power of x. Now, why am I allowed to do that? Well, because if you divide the top and bottom by the same thing, you're basically dividing by 1. So if I take this x over 2x squared plus 1, the highest power of x in this particular fraction is x squared. So can I divide the top by x squared? And can I divide the bottom by x squared? Because effectively, I'm then dividing by 1. Because I'm dividing by the same thing. So I'm effectively dividing by 1. So I haven't actually changed the question, because we were not allowed to do that. So now, what does this mean? Well, the limit as x tends to infinity of, well, x over x squared would be 1 over x. 2x at the bottom here, 2x divided by x squared would be 2. And 1 divided by x squared will be 1 over x squared. Now, what happens here is we now take the limit as x tends to infinity. And the theory behind this is, as x tends to infinity, 1 over x will tend towards 0. Because 1 divided by an absolutely massive number will be 0. And 1 divided by x squared will tend to 0 even faster than that. So basically, both of these tend to 0. So this tends towards, okay, remember, a limit doesn't mean you get there, it means you tend towards. So the limit equals, well, it basically equals 0 divided by 2. And 0 divided by 2 is 0. So therefore, y is equal to 0 is the horizontal asymptote. So this is exactly like a hyperbola, because a hyperbola tends towards a horizontal asymptote, and in this case y equals 0 would be the x-axis. So this graph, whatever this graph looks like, as x tends to infinity and as x tends to negative infinity, this graph is going to tend towards the x-axis. Now, fortunately, we very soon are going to plot these functions, and then we can actually see what they look like, which is pretty cool. So, just to note, because we need to pick up a trend, what do we notice about this? We notice that the highest exponents of x was on the bottom, and the bottom was 1 bigger than the top. So let's just try and pick up a trend. Okay, let's look at example 2. Example 2 says, f of x equals 3x over 2x plus 4. My question would be, does this have a horizontal asymptote? Well, to answer that, we'd have to ask ourselves, can we work out the limit as x tends to infinity of this function? Well, let's check. That's the limit as x tends to infinity of, and the highest power of x in this particular question is 1. So I'm going to divide the top by x, and I'm going to divide the bottom by x. So 3x over x is 3, 2x over x is 2, and 4 over x is 4 over x. Now what happens is, 4 divided by x is going to tend to 0 as x tends to infinity, because 4 divided by an absolutely massive number is 0. So this will tend towards 3 over 2. So therefore, y is equal to 3 over 2 is the horizontal asymptote. Simply because as x tends to infinity, the graph will tend to y is equal to 3 over 2. Now notice in this case, the degree on the top and the degree on the bottom were equal. There were an equal number of x's. Now, what happens when there's the same amount of x's on the top as in the bottom? So I mean the degree, the highest power. What happens is, do you notice you get a constant and a constant? Because you divided by x and the x has disappeared. So you start to get really good at this once you've practiced, because you start being able to realize that this will be tending towards 3 over 2. You also start to be able to look at this and say, well, if the bottom has a higher exponent than the top, then the top is always going to tend to 0, because it doesn't matter what you divide by, this top is always going to have some x's at the bottom because it had fewer x's to start with. And so you start getting used to the fact that if there's a higher degree on the bottom, your asymptote lands up being at 0. Okay, now we're going to discuss that some more, so don't worry if you're not comfortable with that. So this particular one, let's have a look. First things first, do you notice that the degree at the bottom is bigger than the degree at the top? So immediately I can tell that when I find the limit as x tends to infinity of 2x plus 6 over x squared minus 9, you divide by the highest power of x. So I'm going to be dividing by x squared. So guess what happens at the top? Quite predictably, this becomes 2 over x, and this becomes 6 over x squared. Now what are both of those going to tend towards? Both of those are going to tend towards 0. So even though this is now going to be 1, because it's x squared over x squared, notice, thank goodness the bottom isn't 0, because if the bottom's 0, I have a problem, because then this limit doesn't exist. So this does exist, but it's 0. So therefore, hopefully we're getting used to this. Y is equal to 0 is the horizontal asymptote. Now, what other trend have we picked up? Notice I haven't done a single example of where the degree at the top is bigger than the degree at the bottom. Now, why? If the degree at the top is bigger, if the degree at the top is greater than the degree at the bottom, what would happen? So let me just write down an example. What happens if we had x cubed plus 1 over x squared plus 3x? You would end up dividing always by the highest power of x. So you would divide this by x cubed at the top, and you divide by x cubed at the bottom. So this would be 1 plus 1 over x cubed, and this would be 1 over x, because x squared divided by x cubed would be 1 over x, and this would be 3 over x squared. And look what happens. Both of those would tend towards 0, and this limit would not exist. So it makes complete sense that you have to have a higher degree at the bottom than at the top, or the degrees have to be equal. If the degrees are equal, then the limit actually just becomes the ratio of these coefficients. If the degree at the bottom is bigger, then the limit is always just 0. But you can never have a degree at the top that's bigger than the bottom. I hope that kind of makes sense. So I've written that myself a little note here that says that type of thing. Note, if f of x equals g of x over h of x, you've got two functions, one at the top, one at the bottom. There will be a horizontal asymptote if the degree of g of x has to be less than or equal to the degree of h of x. So the bottom has to have an equal or higher degree than the top. If they have an equal degree, then it just becomes the horizontal asymptote actually always works out to the ratio of the coefficients. If the degree at the bottom is bigger, then you actually always get y is equal to 0. Now, I wouldn't worry about remembering that, because you kind of, finding the limit is a very quick thing. It's just nice that when you get the answer, you're like, oh no, that makes complete sense. Okay, so those are the first two of the asymptotes. We should have done them in grade 11, and so this should be kind of a little bit of revision, but we never actually started drawing these functions in grade 11, and so this was quite theoretical. Now, I'm going to end the video because the last type of asymptote is an oblique asymptote, which definitely takes a little bit longer to explain. So to avoid making this so long, too long, we're going to leave it as the first two. So we should now understand vertical asymptotes, removable discontinuities, and horizontal asymptotes. Cool.